Hi, this is the presentation of the paper, PAME, Precision-Aware Multi-Axis DNN Serving for Reducing Latencies of Batched Inferences, in ICS 2022. I am the first author, Zhang. This paper focuses on the inference phase of DNNs, deep neural networks. DNN inference is the base of most AI applications nowadays, and researchers are pursuing extremely short latency in DNN inference services. There is an observation that different efforts are required for the inference queries to achieve sufficient precision. For example, in the task of image classification, there are so-called easy samples that do not require much effort to achieve a correct result, and hard samples on the contrary. So, it is intuitive to let simple inferences exit early from the DNN model and only let complex inferences go through the entire complex DNN model. And this is called the early exit method in DNN. The difference between samples is common, and we testify the effectiveness of early exit in various tasks, including image classification, semantic segmentation, pose estimation, language models, and so on. And in this figure, the horizontal lines show the inference precision of the original DNN models, and the x-axis shows the exit position. And as observed, the precision of some early exits is close to the original precision. For instance, if the exit after the sixth block is adopted for the SST2 task, the precision can reach 98% of the final exit precision, but the computation is halved. We can also observe that for the cityscapes task, the precision is even 3% higher than the original precision if the queries exit earlier after the 28th block. So in this case, using only part of the whole model is more efficient and can also achieve satisfying results. Although in most cases the precision will be reduced if all queries return from the early exit, it is potential that we can anyhow reduce the latency by allowing some queries to exit early while still promising a satisfying precision. And in current DNN serving systems, there is another observation that to fully utilize the hardware resource, inferences are often processed in batches in accelerators like GPUs. Like this figure, inference queries are often collected and organized in batches. Then a batch is delivered to the accelerator to compute, which means that all the queries have to return at the same time. Thus, we designed PAME to allow different samples within a batch to exit from different exits. Note that PAME has two objectives. First, PAME should be precision-aware, which means that this multi-exit design should not harm the precision of the original service. The second objective is to reduce the average latencies of batched inferences. To attach access to the original DNN model to achieve such objectives, there are three main challenges. The first challenge is the exit structure, which is also how to design access. We have promised the early access to be as good as the final exit, and thus the parameters in exit should be redistributed through special training schemes. The components in an exit, including the bridge as well as the functional head, should all be well designed. Second, we have to decide where to attach access, which is the exit placement problem. It is computationally challenging to find out the optimal network architecture because the complexity of the search space is huge. It is necessary to design an efficient method to find the optimal access to minimize the latency. What's more, the additional computation of access may bring overhead and extend the latency of inferences that do not exit early. And as shown in this figure, the computation cost in functional heads is very different, and in some tasks, the computation of heads can take a very large proportion, bringing risks in increasing latency. Like this ResNet and the simple combination, which is used for post-estimation, the head requires 70% multiply accumulate operations of the backbone. And here is the design of PAME. This illustration shows how we attach an exit on an original single-exit ResNet model. The original single-exit backbone is in purple, and it is composed of many individual blocks. And by attaching an exit at the exit point, the original model is separated into two stages. In practice, each stage is assigned an inference engine, and there is control flow and data movement between those two stages to deliver the unfinished data from the last stage to the next stage. And before determining the final used axis, we first select some axes equidistantly alongside the backbone to form the exit candidates. And here we are going to introduce the common structure of the axis. And for each exit candidate, there are three components. First is the bridge, which is responsible to transform the intermediate feature map to the required form of the head. To minimize the bridge overhead, while still making sure the bridge can achieve its basic functionality, the bridge intimates the original backbone and copies the parameters. Second, for the head, we also copy the parameters from the original head. Then we perform transfer learning to fine-tune the parameters in the backbone, the bridge, and the heads. Third, the exit check structure is responsible to decide whether an input query in the batch should return from the exit or not. And it generates the control flow to decide what data should be copied to the buffer of the next inference engine. The exit check structure is composed of two modules. As a rule-based procedure, the dimension reduction step first selects the principal values from the output values. Then, in the threshold check step, it compares the principal values with two thresholds, which are the confidence threshold and the count threshold. So, there are two thresholds that need to be determined to promise the precision of queries that return from the exit. And this exit candidate configuration process is achieved by brute force searching. Then the qualified thresholds can be finally determined as shown in this figure. And now, after settling down the structure of axis, we now try to find where should we attach axis to best reduce latencies. Note that the placements of axis should be dependent on the pattern of flows, because queries with different difficulties should return from different axes adaptively. And we decouple the profiling of the inference time and the input loads to avoid the mixed cumbersome profiling. We record the profiling results in two matrices, and the first one is the inference time matrix. In this matrix, we record the two-stage inference latency at different batch sizes. We compare the two-stage inference time with the original inference time. The green area indicates that with such batch sizes, the two-stage inference has shorter latency compared to the original one-stage inference, while the red area indicates that the latency is violated. Thus, only when the batch size of the second stage falls into the green area, the corresponding exit would be feasible. The second matrix is the batching pattern matrix. It records the batching pattern of loads. It reviews the exit distribution of numerous batches at different axes. If in many batches of current load, the proportion of queries that exit early is not large, then many batches would face latency violation. As shown in this figure, the batches that fall into the red area in the inference time matrix would face latency violation and cause this exit not applicable. Finally, according to the inference time matrix and the batching pattern matrix, the average latency with each exit candidate is estimated, and we select the exit with the shortest average latency. And in this example, the exit E4 is selected. Note that this is only one step in the exit searching procedure, and only one exit is determined. After determining an exit, we recursively search for more exits among the remaining exit candidates by separating the backbone after the determined exit into two stages. Here are the exits found by PAME in different tasks. After the recursive exit searching procedure, in most cases, one or two early exits are selected to reduce the inference latency. And we have evaluated PAME in different tasks with different batch sizes. And on average, PAME can reduce the average latency by 39.9% while keeping 99.86% of the original inference precision. We have verified the effectiveness of the exit selection method in PAME. And in practice, among all exit candidates, PAME can successfully select the exit with the shortest latency. And this is an example in the ImageNet classification task. And as shown in this figure, the fifth exit candidate has the shortest latency. And since the exits are selected according to the inference time matrix, we can find that in different tasks and with different models, the inference time matrix varies, and its properties largely depend on the computational overhead of the functional heads. And in the task of post-estimation, PAME requires a large proportion of queries to exit early to promise the tail latency is not increased, because the computational cost of exits is huge. In many cases, according to our findings, with regard to the number of exits, more is not better. And as we can see, the moving on ratio after the first exit has already been lower than 50%, which means that more than half the queries can return from the first exit, and then it may not be necessary to attach more exits. In the experiment below, we show that with two early exits, the latency reduction is not prominent compared to the inference with only one early exit. And PAME is adaptive to different loads because the selection of exits is highly related to the pattern of input loads. And as shown in this experiment, PAME is running normally with the current ImageNet load. If the load is changed into a subdataset of ImageNet, then the moving on queries would be more than expected and the latency would be violated. And in this case, by changing to a posterior exit, the pattern of batches would return to normal. And in another case, if the load is changed into another subdataset of ImageNet, ImageWoof, then moving on queries would be less than expected, and the precision may not be promised. Thus, by adjusting the thresholds, PAME can also return to normal. And once the input pattern change is observed, the adjustment can be done based on the inference time matrix and batching pattern matrix directly. PAME attaches axes by separating a complete model into separate stages, and the additional computation of axes is inevitable. Overall, the execution of models takes up to 98.9% of the total inference time, and the exit check phase only occupies 0.1% of the total inference time, and the data movement occupies 1% on average. And here comes to the conclusions. In this work, we propose a precision-aware mechanism to attach multiple axes on DNN models to reduce latencies. First, we determine the axis structure by designing bridges, heads, and axis check structures separately. And second, we apply a method to determine the to-be-used axis based on input patterns. And third, we take the exit overhead into consideration, and the tail latency of a batch is then not increased. And overall, PAME achieves up to 51.4% latency reduction while maintaining 99.68% precision of original models on average. So thanks for listening. If you have any questions or comments, please contact me. Thank you.